Uh, Welcome everyone to the full session of the analysis seminar. It's a great pleasure to introduce the first speaker, Yannick Sire from Johns Hopkins. He will speak on harmonic maps with free boundary and beyond. Yannick?
Thanks a lot for the invitation. I hope that next time could be in person. So I'm going to talk about like a bunch of recent results related to harmonic maps with free boundary, and in particular their heat flow, and then because there has been a revival in the theory of harmonic map with free boundary. So basically I will explain why it's quite interesting to study this type of model. So let me start with what is like a standard harmonic map. So you take like two closed, so by this I mean like compact without boundary Riemannian manifolds, and you assume that the target, so for me the target will be N and the domain will be M, is you embed it isometrically into like an Euclidean space, and you consider the energy, the following energy, the usual Dirichlet energy. And if you look at critical points of this energy, this is the harmonic map equation. And formally, if you are smooth enough, it will solve this equation. So A is second fundamental form of the embedding. So you see that here you have a critical equation because you being bounded, right? Since you are like in the target is closed manifold. So you being bounded, this is like a gradient U square, right? And so it scales like the Laplacian, right? So basically this tells you that if you take an H1 solution, the Laplacian obtained by minimization, for instance, like provided you solve, for instance, a Dirichlet problem locally, then you would get like the Laplacian is in L1, right? So you are like right away, besides any existence theory, you see that you are not necessarily manipulating objects which are smooth. Actually, when the domain is like one dimensional, this is a geodesic equation that you are like looking at. Okay, so this is the high dimensional version of the geodesic problem. So this problem has been extensively studied over like many decades. Here there are a few names, but there are like almost infinitely many others, okay, besides them. So it's a very several aspects I will have the occasion to mention, like why this type of problem has been exciting people all over the years. So basically, as I was alluding, one of the question is the existence, okay? Because
Yannick, I have a question already.
Sorry?
I have a question already.
Oh, okay.
Yeah, so the gradient here is, I mean, the Dirichlet energy, it's using the component function in RK, right? It's the sum of these. Right?
Yeah.
It's not like an intrinsic energy.
No.
It depends on the embedding, yeah?
Yeah. Okay,
thank you.
So then, as I was mentioning, like one of the question would be like one of the question would be the existence, and one way we can construct the existence with this equation would be like to look at the formal gradient flow of this energy. I mean, the modern language. So this is like what Ilse and Sampson introduced, like the heat flow method or negative gradient flow of the energy. So you look at basically like the heat equation associated to this energy, and you start with a smooth initial data, but you could, of course, as less. And you hope that under some conditions, or no condition, but actually there are conditions, you hope that you have a globally defined function, solution of the flow, which is smooth in some sense and converging whenever t goes to infinity to a stationary solution, right? This is like the usual gradient flow. The thing is that you know how to prove that only if all the sectional curvatures are non-negative of the target, this is the first result of Hills and Samson. You can like relax it a little bit by admitting that the universal cover of the target admits a strictly convex function with a good
non-negative or non-positive?
Non-positive, sorry.
Non-positive, okay.
The contrary to several problems, like the negative case is in the target is like the favorable one. So then actually, like when you look at when the target is a sphere, right? Then of course, like you are not under this situation. And what happens is that you can construct a global weak solution, which is only partially smooth in the sense that it's going to be C infinity outside of a set of a closed set, or outside of a singular set in space and in time. So this is like several results by Struve, Chang, Chen Struve, Chen Lin, and many people after that. And so the question is like, what's happening to the flow? Okay, is there like development of finite time singularities in a kind of generic sense, infinite time blow up, or this type of thing? And if it blows up at finite time or at infinite time, like how does it blow up? Okay, so the best result I know about that. So the first result, like the first paper exhibiting like a non-trivial finite time blow up is a famous paper of Chang, Bing, and Ye. And then the best one who actually investigate, I mean, the latest, I mean, the up-to-date result is like a recent paper at Invenciones of Davila, Del Pino, and Way. So why studying harmonic maps? Well, harmonic maps actually are like an instance of appear in a lot of geometric problems. One of them is when you look at extremal metrics on surfaces. So basically, you look at metrics which are like a critical point, let's say, or soup of this spectral function. Also, you take the spectrum associated to the Laplacian on a closed surface, and you renormalize by the area of the surface. And you look at a soup, and actually, like what you can prove is that if the metric is sufficiently regular, then there is indeed, if the metric is, if the manifold, is the metric maximizing, the lambda one, the first eigenvalue is sufficiently regular, then the manifold with this metric is isometric to a minimal branch, minimal submanifold of the Euclidean sphere. And more precisely, what you know is that there is a finite number of eigenvectors that you can exhibit from the lambda one, which are actually like an harmonic map from your surface with your extremal metric, the one realizing the soup of the spectral functional, into the round sphere. So the thing that, so harmonic maps are a tool to understand what are like extremal metrics. But I mean, this is just one instance because it was a convenient one to introduce that for what I'm going to talk afterwards, harmonic map with free boundary, where harmonic maps like play like an important role. But if you look at rigidity theorems, for example, like on Euclidean, you know, like a building or like on complex manifold and so on, or many of the tools, many of the results to get like rigidity have been obtained through harmonic map argument. So it's a very natural tool in geometric analysis, at least like it happens very often. So it's like, so let's look at what's happening with what I call like a harmonic map with free boundary. Or let's look like actually like when the domain has a boundary. So let's take like a boundary domain which has a boundary M, non-empty, and is again my target. And let's take like sigma to be like a submanifold of the target. But sigma has no boundary, and the target has no boundary either. So now, of course, like in the same way that in the case of harmonic maps, I have to because I don't have a Dirichlet problem, I have to identify I have to do like, I have to identify harmonic map to homotopy. So here you look at, since you have a boundary, a relative or relative homotopy classes. And what happens when you look at the following constraint harmonic map problem, you look at the infimum, or, you know, like a critical point of the same Dirichlet energy, but now you want to constrain the problem that the image of the boundary of the domain stick to the a given submanifold sigma of the target, right? So think about sigma being S1 and n being S2, okay, for instance, okay. So then the harmonic map problem that you get is, well, you're gonna have like an like the harmonic map equation inside, then the constraint, and the Neumann derivative has to be, so this is a geometric condition, the Neumann derivative has to be orthogonal to the tangent at sigma, at the, of sigma at the point u of x being on the boundary of omega. So on the boundary of m, sorry. Of the
is it a little bit like a soap bubble, like on a wire?
So, okay, so it's more like a minimal surface with free boundaries. So it's like a codimension. If you want a soap, you would like to have higher codimension, right? Because here, like what would be, well, yeah, this is what you are thinking is that you are spanning a minimal surface given. Okay, so I think I understand what you mean. The soap, the wire would be like a sigma manifold, right?
Possibly, yes. But maybe my dimensions are off. So
yeah. Well, the thing is that, like, in the same way, like harmonic maps of surfaces, like are a tool to generate branch minimal submanifolds into the target. This is more of a system generating branch minimal surfaces on the target, but with free boundaries. So basically, you have to imagine that you have the ball B3, you have S2 to be the boundary. You have a minimal surface inside the ball hitting orthogonally. S2.
Okay. Mm-hmm.
So this is not a sub bubble, really. Like
okay.
Yeah. Mm-hmm. But this is the term of free boundary is kind of misleading, because this is not really a free boundary problem in the way I understand it, in the sense that the domain is unknown. This is really more of a constraint problem, actually. Mm-hmm. And actually, like many people call it like a partially constrained problem, partially like harmonic map, partially constrained harmonic map. And they've been studied by a lot of people. Actually, if you open the old book of Hildebrandt and Tromba in minimal surface theory, they will talk already of harmonic maps with free boundary. There are like many results, and the reason why, I mean, one of the instances where this type of object appears is when you do exactly, you try to understand what extremal metrics. No, not now on a closed manifold for the Laplace-Beltrami, but for the Steklov problem. So that's why I was talking before about like the link between classical harmonic maps and extremal metric on closed surfaces, because like Fraser and Shane actually like develop like a very like strong analogy. I mean, like the exact theorem that I stated here, but in like whenever you have a surface with boundary, they showed that if you endow your manifold with boundary, your surface with boundary with an extremal metric, like for the Steklov spectrum, then actually you generate actually an harmonic map. This is associated naturally with an harmonic map with free boundary. So they pop up in this type of problem. But actually, there are also many problems in mathematical physics, like for example, in the theory of liquid crystals, or in crystal growth, or where you can actually also it's a very natural boundary condition appearing in liquid crystals, for instance. So it's not just a mathematical game. This is what I wanted to mention. So let's look like this problem of harmonic map with free boundary a little bit closer. So let's take my domain to be the half space. So very quickly, I'm gonna forget about like particularly at the elliptic level, I'm gonna forget about like existence result, and I'm gonna look at some regularity, okay, issues. So let's look at when the domain is the half space, and my target is RL, and my sigma is a sphere, okay? So then the problem that I'm looking at is I'm harmonic in the half space. The image of the boundary of the half space, which is Rn, has to be constrained to stay into the sphere, and UD nu has to be orthogonal to the tangent. This is exactly in this geometric setting. This is exactly this equation. Sorry, I missed it. This is exactly this equation when M is a half space, sigma is a sphere, and N is just the Euclidean RL. So actually, like you have an harmonic function in the half space. So if you take the trace of U, actually, like which I did not V, but here, but which I will call U afterwards. So this U is actually a V. So this is a trace of an harmonic function on the half space. I mean, by just Fourier, you can prove very easily that this is the square root of the Laplacian of V. This condition reinterprets into square root of the Laplacian of V orthogonal to the tangent at the sphere of V on the boundary. So actually, like what you are doing is just like looking at the solution of this equation and harmonically extending it to the half space. This is exactly what this system is giving you. The thing is that this equation has been introduced like several years ago, like in the mid, what was it, like 2000, I think, by Dalio and Francesca Dalio and Tristan Rivière. Their idea like was, so the theory of harmonic maps, so let me try to mention why they introduced like this, this equation. The idea of, let me come back to the problem of harmonic maps. So as I was mentioning, there is you have a regularity issue right away here, because the problem is that like if you take like a minimizing if you take a minimizing map, well, of course, for minimizing you can also use other arguments. But if you take a critical point, a weak harmonic map, an H1 solution of this equation, then automatically you have the Laplacian, which is in L1. So L1 is of course like borderline for Calderon-Zygmunt, and you cannot say anything about the regularity of the solution. So actually, it happened that by a breakthrough result of Hélin of the beginning of the 90s, he exhibited like an integrability by integrability by compensation phenomenon on the right-hand side, in the sense that there is an algebraic structure of the equation which allows you to gain regularity. There is a diff-curl lemma behind, actually. He didn't formulate it this way, but there is like at that time for the first paper, this is diff-curl lemma. So there is like a compensation. And this compensation works only in dimension 2. In dimension 3, you become supercritical. In dimension 2, this functional is invariant under Möbius, is invariant under conformal transformations, okay? So yeah, the problem is critical, okay? So in dimension 3, it becomes supercritical. So the thing is that, okay, the problem is supercritical, but can I cook up like a model, an equation, or an energy, if you want, so that my problem is critical in 1D, okay? In the sense that it's going to be like, you're going to have like the same type of diff curl or the same type of integrability by compensation for an equation, but in 1 dimension or in 3 dimension or whatever, but at least in odd dimension. It was the original motivation of Dalio and Rivière. Okay, so the original motivation of Dallot and Rivière was introducing an equation, which happens to be, this is a link that we made with Vincent Millot in 2000, like I don't remember when it appeared, this paper, 2015 or so. It's actually like the trace of an harmonic map with free boundary. But Dallot and Rivière actually looked at exactly this equation directly. So the thing is that, so they proved Dallot and Rivière using like the theory of, I mean, a diff curl. They proved that solution of this equation, even if this equation is also critical in H1 half of the real line, okay, n equal to 1, they proved that if for n equal to 1, this is like solution of this equation is C alpha, the continuous. It's not like an ODE, even if it's in one dimension, because this operator is a Fourier multiplier, okay? Not like a differential operator. So basically, they happen like using this, the harmonic extension, it becomes an harmonic map with free boundary, and this has been studied before, actually. So basically, one could get like their result, like, but they had like some sort of so intrinsic so basically, what I meant to say by this kind of digression, which is not a digression, is that there are always two ways to see harmonic map with free boundary. There is like this way, which is the original geometric way, and there is like this way, like writing an equation on the boundary where actually everything happens, because if you, as soon as you take like the domain, the target N to be an Euclidean space, okay, and you take any submanifold, not necessarily of sphere, like embedding into this Euclidean space, then you have like always an harmonic function and something which is geometrically is this constraint, right? So there are examples actually of half harmonic map. Okay, so Dallot and Rivière called these harmonic maps half harmonic map. It happened that they actually like exactly looking at this energy, sorry, but not the H1 energy, but the H1 half dot energy. So that's why they call it half harmonic maps. So actually, like there are examples of half harmonic maps. So the stereographic projection is an half harmonic map. Okay, so in particular, whose energy is pi. Actually, you can even classify all of them from R into S1. They are all given degree of Blaschke products, so like finite Blaschke products of degree D, when the degree of the harmonic map is D, and you can, it is quantized, the energy is quantized, and so because of what I said earlier, right? This, if you take the harmonic map, this half harmonic map from R into S1 or from the circle into the circle, and you extend it harmonically, okay, then you're going to have like a solution of this equation exactly in the way I described before. Okay. So in the same way that classical harmonic maps are related to minimal surfaces, you can also relate like the image by the harmonic extension of a half harmonic map. The image of the whole half space is going to be a minimal surface into sigma, okay, and spanned by this U of R, U of the boundary. This is exactly the picture that I was describing to Dima. Imagine that you have the three ball, S2, okay, you're going to have a minimal surface into the three ball, okay, but like what's going to hit orthogonally, this is this condition, the sphere, okay, then spell that sphere. Okay, so the theory, like, so there is now the question, okay, let's try to construct like, so let me mention that, of course, minimal surfaces with free boundary are also a very old topic. I mean, there are like many conjectures still holding of minimal, what are like free boundary disks. and the behavior of free boundary disk right before, like going back to the, I don't know, the 50s with Nietzsche and Hildebrand and so on. So it's a very old topic. But all of this is a kind of a new formulation, if you want, more recent formulation of this problem. So let's look at what should be the heat flow. Well, so the thing is that there are two possible gradient flows that you can look at. So here I wrote it. So you can take the gradient flow of the H1/2 energy, and you have distributionally, you have this equation. This is like the heat flow to construct half harmonic map. And if I have a half harmonic map, I have like an harmonic map with free boundary by just extending it harmonically. Well, the problem is that this flow is like dissipating and so on. But the thing is that it has no, well, not that I'm aware of, I should say, monotonicity formula. Okay, like a major, like a tool in all of these geometric variational problems, one way or another, is to get some monotonicity. Whatever elliptic result you look like, or whatever parabolic result you look like you look at, like you need, I mean, if you want to prove something which is non-trivial, you need to have some sort of monotonicity. Just, so this flow, I will call it the bad flow. The bad flow because like I have like no I don't know how to prove monotonicity. Though there is another flow that we could look at, is instead of looking at, so this is a Koshi operator, okay? You know, people in harmonic analysis call the Koshi operator, like it's dt plus square root of the Laplacian is like the Koshi, the Poisson semigroup, I think it's called. And this is, in probability is like the solution of that. So an mental solution of this operator is like the Koshi law. So it's a heavy tail law. But there is another one I could look at. Well, you could look at the square root of the whole heat operator. Well, this you can always define it, okay, using Fourier Laplace and company. And actually you have even like a formula with an explicit kernel. And the thing is that, of course, like if you look at stationary solution of both flows, they are the same. Both of them harmonic, half harmonic map, and then harmonic map with free boundary. Now, this one is much better because this one appears as this flow appears as the trace of not this time an harmonic function, but a caloric function. You solve the heat equation with your constraint, with your free boundary condition, and actually the trace at y equal to 0 of this function capital U is a solution of this flow. Well, you have to put the correct spaces, of course, but this flow is a very nice one because this flow, because you have the heat equation inside, okay, the half space, has monotonicity. So I will show you like what I mean by monotonicity. This is like exactly like the Struve-Whisken monotonicity, an analog of the Struve-Whisken monotonicity formula. So now you are much happier because you can think that you're not going to prove like trivial results because like now it's like you can develop a whole machinery. But you see like the problem is a nonlinear problem on the boundary, right? Because you are caloric inside, okay? Heat equation equal to 0 with your free boundary condition, which is like the nonlinear boundary condition.
Yannick, I have a question.
Mm-hmm.
Is it important that you're setting this up in Euclidean spaces, or is it something you could do in the geometric setting?
Yeah, you can do it like this is put to simplify my life.
Okay.
I'm not claiming that. Okay, so I'm not saying that it's going to be. I'm not claiming that this is what I'm going to say in particular after that. This is a triviality to do that on any manifold with boundary but
in principle, it's
yeah. It's just like I mean, if you want to really like to do the details, it's going to be really technically long and
yeah.
But yeah, it's not that important.
And the fact that the space is, I mean, for compact manifold with boundary, you could also presumably do similar things, or it would be simpler, or, I mean, the fact that it's not compact here plays a role or not?
Well, it depends which such type of analysis you want to do. Because like what I will be constructing is a solution, right, of this flow, which is a weak solution and happens to be smooth everywhere except of the closed set. So depending on which type of analysis you want to have, like for example, if your target, well, okay, let me come back to the classical case. Okay, it's a good question that if you take for the target here to be the hyperbolic plane, there is no finite energy harmonic maps. So this result that I was mentioning here, the fact that you can classify, I mean, the fact that there is no finite energy. If the target is non-compact, you have no finite energy. So how do you define this type of thing? You see, like you can always look at like a critical point of the equation, okay? But of course, you have to be very careful with type when the target is non-compact with which type of solution you are manipulating. And you would have like the same thing here. By the way, you would have the same thing also for the flow of harmonic maps. I mean, like in the sense that you have to be, I don't think that it's been much studied, like the case when the target is non-compact. And like it's been very little, like even like talking about the Yamabe flow, for example, I know very little results about like the Yamabe flow on non-compact manifolds, or even like solving the Yamabe problem as an elliptic or non-compact manifold. I know that there are, well, like here there are obstructions and so on, but actually like it's not been studied much. Yeah. I will come back to that a little bit later when I talk about like singular manifolds. So basically now what we would like to prove is, so one way to construct weak solution, and what I will call a weak solution, okay, there is like or a Struve solution. I mean, what I would call a weak solution is a solution given by a Ginzburg-Landau approximation scheme. So you are penalizing your parabolic problem, right, with the Ginzburg-Landau potential. If the target is not if the sigma is not the sphere but the general manifold, you have to project and so on. But you can do it, okay. You can also like have like a Ginzburg-Landau approximation scheme been known by Chen and Struve, okay. But let's focus on when the target is a sphere. Actually, when the target is like any other like compact manifold, not the sphere, like it's just technically harder to write the thing, but now we know how to do it. And so basically, like you have this energy, okay, it's formal energy. And of course, like by classical parabolic theory, almost classical parabolic theory, for epsilon positive, you have like a smooth solution of this flow. It's almost classical because here you have like a nonlinear Neumann boundary condition. So it's not completely, doesn't fit into, but well, there is like a smooth solution as expected, and you want to send epsilon to 0. This is what you want to do. Because of course, like when epsilon goes to 0, you would like you would like to see the sphere appearing, because if you want to stay at finite energy, for instance, you would like to stay this. You have to, for this term not to blow up, you necessarily need to see mod u equal to 1. So you necessarily in the limit have to be on the sphere, right? Well, this is what we proved. So I think that the paper should be out on archive like anytime soon. We are finishing the last correction. So basically, if so I wrote it like even when the target is more general, but think about the sphere. So there exists a solution which is an infinity in time, I mean a weak solution, H1 with a derivative which is in time, which is like so strong solution in the language of parabolic equation, L2 function, satisfying this in the distributional sense, such that it comes as a weak limit of U epsilon, where this limit is actually strong in C2 alpha, away from a singular set. The single, of course, the singular set is on the boundary, right? Here you are caloric, cannot happen anything, nothing can happen inside, right? This is a heat equation, everything has to be smooth inside. And so it's like the singular set where you're going to have blow up, or the solution will be singular in space and time with finite parabolic measure, okay, parabolic Hausdorff measure. And the trace of this thing is, so if you look at really like the flow of harmonic map, and the trace of this thing is happens to be like smooth away from this singular set and satisfying this half harmonic heat flow, or like heat flow, or like the heat flow of harmonic free boundary, whatever you call it. Yeah, and so basically, so you have like what is the classical, well, one of the possible results is that this type of partial regularity result. So this is what I call partial regularity, right? Your solution, U epsilon, U star, is smooth outside of a singular set, okay, of small measure. And the thing is that you can prove a small energy regularity if the energy of the initial data is small enough. Then actually the solution happens to be everywhere smooth. So this is something which was already understood for the heat flow of harmonic maps. Not in the original paper of Hills and Samson, they didn't have like the tools, but after that, this is the concentration of energy contributing to the appearance of singularity. Okay, so the singular set, this epsilon naught here, the singular set is basically the set in space and time, such that this energy E here is well, or like a version of it is large, is bigger than this epsilon naught, because smaller than this epsilon naught, and by monotonicity you have like full regularity. So this is a classical result, like in geometric analysis. If you have a smallness assumption for the energy, then you have regularity in a smaller domain. Okay. So there are two tools to prove it. So the main thing to prove is this result, actually, because then the rest follows by covering. Well, but the thing is that you can prove this result and the covering behind, like also because you will use two tools. The first tool is a monotonicity formula. So if you take the backward, here there is like yeah, if you take the backward, here there is a look at absolute value. If you take the backward heat kernel, then you multiply that by the terms appearing in your energy. This energy at level epsilon is monotone, non-decreasing in the radius of the parabolic cylinder. And here, this is like a parabolic, this is like in space and time. Well, this is a direct, okay, so this type of formula is not, I mean, this is exactly the same computation you would do for mean curvature flow. Actually, like it's called the Wisken-Struve monotonicity formula in the case of the harmonic map heat flow, because there is like a really like an analogy between the computation you do for mean curvature flow, and which can be for mean curvature flow, and this one. And the second one, well, okay, you have, of course, like the parabolic equation. Even if it's a system, you still have like some versions of the maximum principle. And the second tool that you use, which uses also like some energy, like somehow, I mean, like some energetic argument, is that like is a clearing out lemma. I mean, one of the first instances were put maybe in the paper of Shane and Uhlenbeck, definitely in some papers of Lin and Rivière. The idea is that, well, okay, if I'm at small energy, then I'm not going to be vanishing. So I'm going to be quantitatively in a smaller, possibly parabolic cylinder away from zero. So I'm going to be bigger than 1/2, say. So if I'm small enough, I'm going to be away from the wells of the potential, which are like modulus of away from the trivial phase, u epsilon equal to 0. Well, but how, well, this type of cleaning out lemma is like everywhere in this type of theory, like for harmonic map flow, Ginzburg-Landau, and so on. And this is very useful because, so this is like a sketch of the proof, but this is very useful because if you have that, then you are good to go because you can do a polar decomposition, right? Because in a small enough energy, you have like, you are away from zero, so you can define this quantity, the angle, and the modulus, right? But the modulus satisfies like a nice scalar equation, and the angle will satisfy like a bad equation somehow, but with Neumann 0. The thing is that if you have this, you manage to derive uniform gradient estimate. And once you have the gradient estimate in space and time, this means that you are controlling this term here, then you are good to go. This is like you are control. You have really a point-wise gradient estimate, right? This is a C1 alpha estimate. Well, uniform in epsilon. Well, so you have to work a little bit to do that, and then once you have that, you manage to pass to the limit. Epsilon goes to 0 actually, and get exactly. Let me put again the theorem, get exactly that. Okay. So the main tool here which makes everything work is the monotonicity. If you don't have monotonicity, I don't know how to prove this type of result. You might be able to prove some sort of small energy regularity, but the partial regularity, it's another thing. So of course, like I mean, actually, like if you I will mention that a little bit later, but if you refine properly, like your analysis, whenever the target is a non-positively curved, okay, then sigma is actually empty. There is no singular set. Okay, so let me put like a few comments about like the previous result. First, I use like some sort of extrinsic version in the sense that I put my n, my target, all the time to be an Euclidean space, okay? So that's why I have an harmonic function or caloric function inside. If you want, you have like another so-called intrinsic version, which being but now the nonlinearity will be inside also, and you have to use other tools to do it. But actually, like, of course, there is a link between the two because like I mean, you can jump one to the other depending on which type of problem you are looking at. Here, don't forget that here's a singular set appears on the boundary, right? Which is like really like where the things happen, right? Like this is like catching really like everything. I mean, this is like intrinsically a boundary problem, right? Because like everything happens on the boundary. Okay. So what people looked at for the harmonic map flow with free boundaries, the intrinsic version, like looked at before, were like a singular perturbation inside, because they were looking at an intrinsic version. Since I was interested by an extrinsic version, so the fact that you consider the target to be always in a Euclidean space, not the constraint, but the target, then you have to design a singular perturbation, which is much more natural, which is on the boundary. And somehow, like, this is a much more natural thing because, like, harmonic map with free, I mean, what happened for harmonic map with free boundary, the interior problem is like the classical one. So really, like, what you are looking at is a boundary, like, effect. So in that paper in the mid or late 90s, like Chen and Lin like raised the following question: whenever like M is a smooth domain of R2 and N is Rn and sigma is a smooth manifold of Rn, is it possible to cook up an initial data such that the harmonic map flow has no global smooth solution, so blows up in finite time? And we could solve this just recently with Junchen Wei and Yuqian Zheng. So the idea is that, like, basically you introduce this parabolic outer gluing where you construct the data such that, like, given k points you give yourself to on the boundary, you will blow up like a half harmonic map. And this is a concentration of the density. So this gradient, well, this has to be introduced like as a measures, right? Weak star measure. And the blow up rate is this one. And the reason why we managed to like construct like one of these non-trivial blow up solutions is because actually like we could reinterpret the solution, our equation, or use tools that have been recently developed when one looks at integral equations of this type, because the flow of that Chen and Lin consider and that we consider happens to be like involving this type of operator. It's really like because of this point of view of okay, either depending on what I want to prove, I go from inside to the boundary or from the boundary to inside, like whatever tool is more convenient, is the most convenient for me. So as I was saying, like alluding a little bit earlier, is that like one can ask, well, what are the obstructions? What are like, sorry, the obstructions, yeah, to a global solution. So what is like, what's happening when you have finite time blow up? Well, in the case of the classical harmonic map heat flow, this is like a famous paper, a series of papers by Shangyu Wang and Francois Lin, where they look at what is the parabolic obstruction. So this is really like a refined blow up analysis on the flow itself, okay? And so basically in this case, in our case also, one can prove that the obstruction are either our harmonic maps with free boundary or possibly self-similar caloric functions. So it's kind of similar. The obstructions to global existence are like related to this one. So to finish, let me just like mention some open problems that I think are interesting. So let me say a few seconds about this bad flow. What I call if you remember, what I call the bad flow is the flow that I didn't like because I couldn't prove any monotonicity formula. Well, it happened that we managed still to prove, so we don't have any kind of regularity or partial regularity of the flow. Constructing weak solution can be done easily, but we're interested like in partial regularity. But we managed nevertheless to prove with the same authors, like not in the same papers, but in the same journal which appears the same year, that this flow has an infinite time blow up. We managed to construct like smooth initial data so that like it has infinite number. But really, it seems that this flow, we conjecture that this flow, because of formal computation, doesn't seem to admit finite time blow-up, contrary to the harmonic map heat flow with free boundary, contrary to the good one. It would be very strange to have such a thing appearing for a critical flow, actually. I think that one of the most interesting thing in the parabolic theory for harmonic maps, and it's actually largely open, even in the classical theory, is how do you construct a weak solution when the target starts being singular? So there is, like in the elliptic case, there is like some famous papers by Koreva and Shane, and after many people like my colleague Chikamedze and Georgios Daskalopoulos. So basically, if you are non-positively curved, okay, in the sense of metric geometry, right, you can, in the target, you can construct nice, a nice elliptic, even for cat1 spaces, even possibly like positively curved, but you can construct a nice elliptic theory. The parabolic theory, except a result which is very cheap, where you construct like a solution by minimizing movement. Nobody knows how to do it. And let me mention that if for those of you who are familiar with what is called now the Caffarelli-Silvestre extension, but where you just replace this operator, harmonic operator, by a weighted operator taking into account, so here you would have like to the power, okay, let me try to find it somewhere, to the power s here. Actually, it seems to be just a mathematical game for s between 0 and 1. And actually, if you work out a little bit the equation, it's a model for manifolds with edge or conical singularities, actually. So it tells you that using this very same type of tool, but changing the operator inside and using like this weighted operator, taking into account the weight up to the boundary, to some power with a suitable range of power of this weight, then you would all the things that I talked about, like can be done more or less like straightforwardly when you put S, not all of them, but when you put this weight, and then it would give you like a theory for harmonic when the domain is a conic manifold, either a conic surface or even like higher dimensional edge type, like the edge S1 in S3, for example, higher codimension. I think I'm going to stop here. Thank you very much.
Thank you very much, Yannick, for a great talk. So, are there any questions?
What is this super rigidity on your last slide?
Oh, this is like the reason why Shane and Koreva studied these maps is when you look at, you can use harmonic maps to prove rigidity of, okay, you want to identify two spaces, right? You want to say that they are the same up to like a diffeomorphism or something like that, or bi-holomorphism or something like that, if you look at. And so the thing is that you assume that an harmonic map allows you to construct like a deformation from one space to another. But if you prove that an harmonic map has to be trivial between the two, then this means that the two objects have to be basically the same because they sit in the same class. So this is like how Koreva and Shane, no, there is a famous paper of Gromov and Shane where they introduce these energies when the target is just a building, an Euclidean building, like some sort of a lattice, that they prove like this type of result. They use harmonic maps to prove rigidity. This is the super rigidity. They call it super rigidity. This is what I mean. I mean, it's a very useful tool to deform an object to another, right? But if you prove that this deformation has to be trivial, this means that the objects are the same, basically, right? And this type of, but to prove that this is trivial, you need to develop like the existence, well, the regularity of the harmonic map, and to prove, I mean, and at the end, I mean, you have to a lot of work because you want to manipulate objects which are, you want to deform smoothly, right? So that's why. I think that this idea goes back to the idea of using harmonic map goes back to Yao and Gromov and for rigidity.
Thank you.
And so this Landau-Ginzburg regularization, you know, epsilon times 1 minus epsilon squared, u minus 1 minus u squared. This is for, so this is, you want your boundary to be on the sphere, right? So if you want your boundary to be on something else, then you need to do something else.
Yeah. Well, then you use a Nash embedding and you project and you get like a distance, you get something which looks like the Ginzburg-Landau. I mean, the only thing that you use of the Ginzburg-Landau is basically the fact that, I mean, let me share again. The important thing that you use of the Ginzburg-Landau is the fact that the energy, the level set of the potential are basically the manifold, where, you see? So manipulating, using the Nash embedding, if you have any closed manifold, when you have like a hypersurface, like the sphere, this is very easy, but if you take any closed manifold using the Nash embedding, you manage to construct like a potential such that the level sets are exactly this manifold that you are looking.
Okay. So you replace Landau-Ginzburg by something else.
Exactly. I still call it Landau-Ginzburg, but this is it's.
Okay, thank you.
Actually, it's not necessarily, depending on what you look at, it's not necessarily easy to look at this type of general Ginzburg-Landau regularizations. But in this case, even like in the classical case, old paper by Struve and Chen, where they look at this type of approximation. And this type of thing, you can do it only if you are smooth. That's why, like in the singular setting, even if like you look at, I mean, like, you know, you could think about like, some Alexandrov space, you know, a length space in the target where like it has like nice comparison. I mean, we don't know how to construct like such an approximation, so that like you have like a nice approximation, so that actually you can do computation, you can have monotonicity, and you can prove like you know, uniform estimate and so on. And so that's the major. That's why when singular you cannot use this type of thing.